Hello and good evening. My name is Gary Billam and I work in the Development and Alumni Relations Office at the university. I'm this evening's host and will introduce you to this evening's star attraction, Professor Sean Elvidge, very soon, so bear with me. This event is part of our Bringing Birmingham to You series, a chance for the Alumni Office to connect Birmingham academics with our global alumni community. We bring together researchers, donors and alumni to highlight the university's impact and its important role in driving progress both academically and in wider society. Events like this are a fantastic opportunity to showcase the incredible work of our academics on a truly global stage. We're really proud to share that our university is now ranked 76th in the world and 11th in the UK in the latest QS World University Rankings, something we should all be very proud of. As you may know, we had originally planned to meet in person this evening. However, due to the travel disruption in London, we made the decision to move the event online. Thank you to everyone who registered for your understanding and flexibility, and we really appreciate it. We hope to be back in London again with another in-person event before Christmas, so please stay tuned. The silver lining, apart from escaping the travel stress and chaos in London, you can enjoy it from your sofa, is that going virtual has allowed us to welcome even more of you from across the world this evening. Please let us know in the chat where you are dialing from. It's almost time for Sean, so please stay with me for a little bit longer. I'm just going to run through a bit of Zoom etiquette before I introduce you to Sean. Just a reminder, this webinar is being recorded. Only the speakers will be captured on the recording. A call to action again, please submit your questions via the Q&A box and we'll do our best to answer those towards the end of the webinar. And please feel free to use the chat function throughout the session. So here we go. This evening, we turn our attention to a topic that some of us may not have heard much about until recently, space weather. As society becomes increasingly dependent on technology, space weather is emerging as one of the major risks we face. One of the most recognizable and awe-inspiring effects of space weather is undoubtedly the aurora, the northern and southern lights. Over the past year, we've been treated to some exceptional displays with increased visibility across the UK. But while these displays are beautiful, they also remind us that space weather poses a serious and growing risk to our modern world, impacting infrastructure, technology, and communications. Although extreme space weather events are rare, when they do happen, the consequences can be severe. That's why the government lists severe space weather as a top-tier natural hazard in the UK National Risk Register. The University of Birmingham is leading the way in this field. So to tell us more about that, what that means and how we're preparing for the risks, I'm pleased to hand over shortly to our expert, Professor Sean Elvidge. Sean is a leading expert in space weather and heads the Space, Environment and Radio Engineering, SERENE in brackets, group at the University of Birmingham. His research focuses on forecasting and mitigating the impacts of space weather on satellite systems, communications and navigation technologies. He has developed pioneering techniques for upper atmosphere modeling and has led major programs to improve operational space weather forecasting. He is the incoming chair of the International Union of Radio Science and a member of the UK Space Environment Impacts Expert Group, regularly advising national agencies, including the Ministry of Defence and the Cabinet Office. Sean is a recipient of the Koga Medal, Gold Medal, and Forbes 30 Under 30 accolade for his scientific contributions. He's also an active science communicator, engaging regularly with media, schools, and the public to raise awareness of the societal relevance of space weather. Sean's going to talk to us for around 25 minutes. I'll open the questions at the end, so please hold on to any questions or reflections you may have until then, or use the Q&A function. So Sean, we're over to you. Enjoy, everybody.
Great. Let's share that, and then hopefully Gary will give me a thumbs up that that has worked. Perfect. Okay, well, good evening, everyone. I was just enjoying there seeing all of the places appear in the chat box where people are from, which is, you know, an intimidatingly wide variety of people. So I'll do my best to try and talk you through all of these bits and pieces in the interest of space weather and the research that we're doing at Birmingham on this area. So as Gary said, so I lead the Space Environment Research Group at the university. We've been running for about 10 years now as a group. So we're sort of mid-age now, I'll say, in research group. But there's lots of more than just me. There's about 25 of us that work on this topic area, and I'll try and give you a really brief flavor of what's going on. So to that end, let's go. So what actually is a space weather? So it all really starts with the sun. Now, we're all familiar with the sun. It's pretty important. In the UK, it's occasionally visible to us, but it is something that, the formation of all of life, so it's fine. What you might find the astronomers describe it as a relatively garden variety star. It's not particularly big, it's not particularly small, it's not particularly hot, it's not particularly cold, it's very average. But whilst it might be very average, it is very active, and it is an evolving, constantly moving thing. So what we've got here is what's really going on in the sun. Well, right in the center, it's clearly a big, giant nuclear fusion reactor with atoms smashing together, releasing energy. And that's happening billions and billions of times over, and that generates the heat and the light. What I'm sort of interested, though, are these big circles that appear just under the hood, as it were, that you can see in this slice. These are giant convection cells, big bits of moving heat and light and energy up and down. And what can happen is, well, actually, bits of the sun can stick out of it. And this little cartoon here is essentially the magnetic field. The sun has its magnetic field that sticks out, and it comes back in and it goes out. When it comes out, it cools the surface a bit, and you get these little black dots. We're going to come back and talk of those in a minute, but it moves in and out. Unfortunately, it doesn't always just do that, and you can get this process where bits break off the surface of it. And that's because the sun is rotating. So we all know that the Earth is going around the sun, and that's very common to us, and we know the Earth spins, but the sun is also rotating. It takes about 27-ish days to rotate once on its axis. But because it's a gas, it rotates at different rates. And it's that rotation, what I want you to imagine is like a big elastic ball band. And what can happen is essentially the elastic bands get pulled and stretched, and that's fine, but sometimes they snap. When they snap, that flings stuff out into space. But by stuff, it's huge amounts of matter. Now, you may have heard in the news things like the word solar flares. Solar flares come up a lot, and they're a thing. We're not really that interested in them because it's actually a thing called a coronal mass ejection that does all the big heavy lifting. Now, these are fast. They move about 1,000 kilometers a second, and they're massive. They're about 10 to the 12 kilograms, which is essentially a meaninglessly large number. The best I can do for a reference is it's about 10 times the total mass of the human population. So a big lump moving very fast through space. And it has a magnetic field. But we also have a magnetic field. The Earth has our own little force field to protect us from all of the stuff that space throws at us. It's why life can evolve and work here. And it has this orientation as it floats around. Unfortunately, if something coming in has exactly the opposite orientation, obviously this is all working in 3D, but I can only show you in 2D, you get this coupling together of the two fields and the dumping of material into the upper atmosphere. And then the solar wind, which is just this constant stream blowing off the sun, is going to force it around the Earth. It's going to do it again, and it's going to push material back to the Earth from the backside as well. And what that is essentially the dumping of energy into the high and low latitudes, and that gives us the aurora. And the aurora is just the excitation. It's just those particles that have come from the sun, follow the magnetic field lines, interacting with the atmosphere, and it makes this beautiful effect. And as Gary said in the introduction there, that's the sort of poster child of space, of the poster child for space weather, because the aurora are incredible. These are a series of videos of all manner of gorgeous aurora all over the place. And that's the pretty side of what we do. And they are the consequence of those geomagnetic storms that are hitting us from the sun. They're not caused by solar flares, but solar flares often are nearby, shall we say, so that will let people off the confusion. Now, what I showed as the video came out was these black dots of activity, and they're the sunspots. They're sunspots. You can see those with binoculars, with an appropriate filter on them. Don't use binoculars to look at the sun, please. But you can observe them from the ground. We see those black spots. We've been observing them since, well, for thousands of years, but regularly since the 1750s. And the amount of activity changes. It goes up and down. And a good sort of proxy for how much the sun is doing at any given time is just by counting how many sunspots there are. When there's almost none, there's very little activity. When there's lots, there's more activity. And that follows a roughly 11-year cycle. And this is just the last sort of 80 years or so of that sunspot activity. You know, lots of colors here, but if you just look at the orange, that's the yearly average number of sunspots. And you can see it's in these roughly 11-year chunks. But also each cycle is not the same. You can see there are some, like in the late 1950s, where there's more activity, followed by a smaller activity one in 1970. Most, you know, so they go up and down. They're not exactly 11. Nothing in physics is that nice. Well, you know, we wish, although if it was that simple, I guess we wouldn't have a job. But it's a messy, complicated environment. But there is all this activity going on. Now, if I zoom in just since the year 2000, you can see where we are at the moment. So on the right-hand side of this plot is 2025, where we are now. And what we are doing is looks like we're just coming down from what we call solar maximum. So a period of time when there has been more sunspot activity and more activity in general from the sun. And what I hope is that a lot of you may have seen the positive side effect of that, which has been the Northern Lights yourself. So there was actually alerts. I know we've got people from all over the world here, but there was there was a minorish event last week where there was pictures of the Northern Lights in the sort of higher regions of the UK. But in May last year, we had a big event, or the biggest event that we've had in 20 years or so. And that gave us aurora all over the UK and all over the world in places that haven't seen it for tremendous amounts of time. We had reports of aurora in South Africa. I'm actually at the UK is hosting a space weather conference this week, which is actually where I am currently. I was speaking to a South African colleague this morning, and they saw the aurora last May. And this is not something that happens regularly in those kind of latitudes. So they are global. Here's a couple of pictures from around the UK of seeing the aurora. It's a fantastic thing. And that coincides with that increase in solar activity. And whilst we're on the way down, it's still quite active at the moment. So I would expect over the coming months and perhaps the next year, there'll still be opportunities to see the sort of this positive side of things. So that's the pretty side. Let me talk to you a bit about what actually is the interest from our point of view. And that's that space weather impacts a whole host of systems and infrastructure and even human health. So this is a picture produced by the European Space Agency, which is trying to, in one thing, show you everything that's going on. That's really hard, but let me talk through a couple of the big ones. Things in space themselves get damaged. You've got a big amount of energy and matter throwing over your spacecraft. Spacecraft are hardened to work in space. The people that built spacecraft are incredibly smart, but if you just dump a load of matter and energy and electronics thrown at it, things go wrong, as you might expect. We also get, as you get closer to Earth, drag effects on satellites. We're going to talk a lot more about that in a minute, so let me park that one there. But as you come closer down, we have radiation impacts. So we are protected. There is always radiation bombarding and hitting the Earth, right? We're protected because we've got a thick, dense atmosphere that's above our heads. But we also like to fly and go places. And as you go, if you go flying, you're going up into the atmosphere a bit higher. That's a little bit less radiation. And if you're doing that during one of these big storms, that's actually a dose of radiation you're going to get extra. And it works out to be about the same as a chest CT scan, a chest X-ray. So it's not an insignificant dosage, especially perhaps if you're doing those routes very often. Then further down on the ground, we have induced currents in power systems. So I showed you that magnetic field that's coming in from the sun. basically that induces electricity to flow through the ground. And that flowing through of electricity can damage our transformers. That can lead to power problems, outages, potentially in the worst and the biggest storms. It impacts a region of the upper atmosphere called the ionosphere. This is a charged part of the upper atmosphere. That's how we do over the horizon communications and HF. So if you imagine a whole community of ham operators, they can communicate over very long distances. They're reflecting signals off the charged atmosphere. It interrupts those. And perhaps the thing that is most familiar to all of us that gets impacted is GPS. Now, GPS is actually, sort of slang. It's the system. We call it, its a formal name is GNSS, but that is a system which is hugely impacted by space weather. We're talking hundreds of meters of errors, which, okay, if you're only using it to navigate your way around the way to the local shops, you can deal with it not working every now and again. But there's a lot of critical national infrastructure that relies on accurate GNSS, including a lot of timing applications, internet banking, a lot of crypto things need accurate timing. GPS gives us that, space weather disrupts that. And that is a huge part, again, of what the group does at Birmingham. I'm going to focus on just two of those things in a minute, but this quick thing on this massive picture of things, I've just circled actually all of the different aspects that Birmingham work on in various degrees to say that we don't do everything in Birmingham, but certainly we are the largest space weather group in the UK, and we try to work across all of these things, but not just in abstract research, but in a way that really helps operations. And I'm going to come out to the end. But what I'm going to focus on is perhaps the thing that is mostly in the news at the moment. Perhaps we should worry most about power. Perhaps you want to worry about PNT, position, navigation, and timing from the GPS. I'm going to talk about space debris and satellite drag, because satellites are in the news all the time now. So let me tell you a bit about what we do for those. And why are they always in the news? Because there's a lot of stuff out there. So this is not a random grab of dots in space. This is an output from one of the products that we produce, which is tracking all objects greater than 10 centimeters in space. So every little dot here is something that we could attribute and has an ID number, and you can follow. You can see, if you eagle-eyed look at the Earth, you might see a few almost straight lines of dots going across the screen at some point. There's one there that's just sort of went through Turkey and going up over there through Russia. Those straight lines, they're the Starlink satellites. Just after they've been deployed from SpaceX, before they go into position, they follow each other for a while, and you can see those going through. So there's a lot of stuff out there. A lot of stuff means things might get a bit messy. So here's a cartoon of why it's interesting, right? So you might think of space as empty, because it mostly is empty. But the satellites that we're looking at here, those ones really close to the Earth, are still close enough to the Earth that there is some air, there is some density around us. So this little cartoon has got just altitude going up from 0 to 500 kilometers. So from the ground up to space, we might consider space starting at about 100 kilometers and then up to 500. And you can see that the amount of density, the amount of stuff in space is decreasing exponentially. That's what this curve's called. So it's getting smaller and smaller as we go up. But where the International Space Station is, where we have various Earth-based observation satellites, where the Starlink constellation, which provide internet to a whole host of people, they're all living in an environment where drag is still a huge problem. Drag is, in fact, the single largest source of error in working out where a satellite's going. So just like a car driving down a road or being on a bike, you feel that brush of air that's pushing you back. That's exactly what's happening in space. We just don't think about it in the same way, but it's absolutely there. And the primary job that we're trying to do is deal with collisions. And that is getting harder and harder. So this is a little plot of the number of things in space, and it's in 4 colors because I'm talking about 4 different regimes, really. So there's low Earth orbit, that's in yellow. That's things less than 2,000 kilometers. And that is where drag and density is still really an important factor that we have to deal with. In terms of the other orbits, we have a thing called medium Earth orbit, geostationary orbit, which you may have heard of, and then sort of above, which is high Earth orbit. And they're all increasing and they're all important. But from a drag environment, it really only impacts into the LEO, the low Earth orbit. And that's where you can see in the plot, it's going crazy. In that post 2020 curve, which is just essentially getting worryingly close to a vertical line, is primarily driven by the launch of mega constellations, Starlink from SpaceX, the Amazon satellites, OneWeb satellites, Chinese constellations. There is a whole host of satellites going up, enabling amazing new capabilities, but it comes with a cost, and that we're going to talk about those costs. But you can see this is unprecedented. We started launching a satellite in 1957. We had pretty steady increase across there, but now it is growing more than ever. What you can perhaps also see around this plot, actually, maybe I can just about use my mouse to show, is little areas where it actually just jumps up as a little spike. And those jumps are from single events which make all of these extra objects appear, essentially collision events, either collisions of satellites, anti-satellite tests, upper rocket body explosions that have accidentally happened, that's dumped a load of things in the atmosphere. And what we want to do is stop that happening. Ultimately, the mission for space weather research around the thermosphere in Birmingham is how do we stop this thing turning into these things? How do we stop those collisions? And this is a challenge because a fleck of paint, so just a fleck of, you might have seen a beautiful launch of an Apollo rocket. Everyone likes to paint their rockets white, in the Americans particularly. A fleck of paint as it falls off in orbit, the energy of that thing moving in orbit has the same energy as a rifle bullet on Earth. So a fleck of paint does serious damage to your satellite. It's like taking a pot shot at it. Anything bigger, centimeter, it's like dropping a hand grenade into it. So even a centimeter piece of object, of which there are many millions, I should say, in this plot I showed previously, these are objects which are 10 centimeters or more. Anything smaller than that, we can't even track from the ground, but we know there are millions of them, and they are colossally, have huge amounts of impact. So what I want to do is give you a sort of example, a sort of case study of the kind of thing of what happens when we go get these things wrong. So Iridium is a satellite constellation. It's a communications satellite. They operate, they're very important. And they have these orbits that are going all around the Earth for their comms links. What we have are also a whole host of defunct old satellites. And what happened back in 2009 was that we predicted that a Iridium satellite would be very close to a Cosmos satellite, and they would miss each other by 584 meters, which is really close in space terms. The problem is we were wrong. And we were wrong by 584 meters, which means that those two things smashed into each other. And this was the first hypervelocity collision of satellites. So these two objects are both moving at about 7 kilometers a second. As soon as you have that impact, it generates thousands of pieces of debris of various scales and sizes, lots of hand grenades now flowing around, which obviously don't just fall to the Earth, stay in orbit. They follow that energy and the momentum that was already there, and they are going round and round and round. Now, in isolation, perhaps we can deal with that. But obviously, as I showed you, there's loads of other things in space. So now we've got all of these uncontrolled things all floating around, and this chance that there could be a more significant follow-on event could lead to a cascade. So this thing crashes into this thing, which crashes into this thing, and that could make the whole of low Earth orbit totally unusable. And this is clearly something we've got to do. Now, we know there are ways to go about doing this. Perhaps we should go and collect all of the junk that's out there. The problem is there's a lot of junk. Now, collection is an important tool, and there are many people that's working out things to do, but we're not going to get everything. We're going to get the worst effects, the big things. There's a thing out there called EnviSat, which is, without exaggeration, the size of a double-decker bus that is tumbling uncontrollable through space. It'll probably stay up there for another hundreds of years, 1,000 years maybe, and it will slowly come back and re-enter. That is a high issue target, which could cause a lot of damage. So we're targeting to go and get those ones. But the little bits of junk that just will be there, we can't go and collect them all. So we need a different way. And that's where we come in. So if you own a satellite, perhaps somebody on the call does own a satellite. If you own a satellite and you want to know where it's going to be, you have to predict that going forward. So you take the satellite, you go, I can see where it is. I've got a radar or I've got GPS and know where it is. I'm going to propagate that forward. I'm going to predict where it's going to be. And what is used currently in the UK is a model produced by Birmingham to give an estimate of where that satellite's going to be. Thing is, we don't know for certain where that is. So we put these errors around it. So imagine you've got two satellites there. We put these circles. Obviously, it's all, again, should be in 3D, which these are ellipsoids, but that's too hard to do. So we've got these circles. And if two circles interact, we say there's a chance of a collision. And we do that for every satellite that's in space. We put the circles around them. We work out where they're going to be. And if they overlap, there's a probability that they are going to interact. And we say, hey, move it out of the way. Problem is, as I hope I've highlighted, it's really hard to do. It's hard to work out where exactly they are. So a lot of the times we say you should move your satellite when you really shouldn't move your satellite. And what we want to do is reduce that uncertainty. So I've drawn these little arrows. Hopefully they've appeared on your screen. Those arrows are a sort of how uncertain we are. And what we want to do is reduce that uncertainty. So we can tell someone, hey, don't move your satellite right now. You don't need to. At the moment, we're probably making on the order of £300 million of unnecessary maneuvers every year because we move things, it lowers the amount of fuel on board, it shortens the lifetime. So that's a thing that we're actively looking to improve. And why is it hard? Well, I showed you a cartoon of what the thermosphere looks like, just this one line going up exponentially. Obviously, real life isn't that easy. Real life, this is what the model does. So we're looking at a whole host of different species. You're looking at helium and oxygen and argon and nitrogen. And then you've got temperatures and how do they all work? At the bottom right, this is what the winds look like at about 100 kilometers. You have loads of continental-sized wind structures blowing things around. So we have to solve for all of these things. We take observations, we merge them together, and we have to do that in a way that can help inform things. So it's a hard problem, which is good. That's what we want. We want hard problems. And this is a little bit of why that's a hard problem. So let me just finish with one thing as a sort of interest, a little sort of quirk almost. So I showed here the kind of species that we're resolving for. These are, complicated things, but they have well-known physical characteristics. What we also have to deal with in the upper atmosphere is carbon dioxide. This is what a typical sort of carbon dioxide concentration looks like. So CO2 is most predominantly down in the lower atmosphere, below 100 kilometers. And then it has this really rapid fall off. And then there's a little bit, left as you go up. And so this is essentially what CO2 looks like in the atmosphere. And what we know is happening is that we're changing the amounts, the concentrations of CO2 in the atmosphere. And that has an interesting consequence in space. So CO2, essentially, the reason CO2 is of such interest to everybody and why it's a problem species for us is that it really likes to radiate its energy. So the sun comes in, it warms up the CO2, and the CO2 likes to spread that out. Now, in the lower atmosphere, that radiating of energy warms up all the other stuff that's around it because there's loads of air around us. Up in the upper atmosphere, there's actually not as much stuff for it to radiate and warm up to. So it still radiates out, but without it radiating to anything, that's sort of spreading out into space. And what that's doing is cooling the Earth's upper atmosphere. So whilst we see warming effects in the lower atmosphere, we see cooling effects in the higher atmosphere. And what that does is it contracts the thermosphere. So the thermosphere is the bit of, the cartoon exponential decay. That's what the satellites are traveling through. That is actually shrinking over time, which means that satellites are experiencing different amount of drag. In this little cartoon, the one on the left, it might have experienced the light blue drag, but now it's experiencing the dark blue because over time, things are shrinking and satellites stay in space for a really long time. And so, again, our models are working at how you predict that. If you're going to plan to build a constellation in the 2040s, let's work out what numbers you should use to plan for that. And so that sort of leads me to just give you my sort of one conclusion slide of what we're doing about it. I mean, I've touched on one tiny topic. All of those little green circles of different impacts of space weather, I could give us a half an hour talk on each one of them. And what we do in Birmingham is try to do the whole chain. We do fundamental research. We're a university. That's what we try to do, right? But that's not only goes so far. So whilst we do the fundamental research, we build the models, we do the modeling, we have the hardcore science, we also run 24/7 operational models. So the UK operational model of the upper atmosphere comes out of Birmingham. We support the National Space Operations Centre, the European Space Agency, US and Canadian governments. We are actively running these things in real time. We're going out into fields, we're collecting data, we're providing that to government, to all manner of governments, so they can make accurate and actionable decisions and then feed that back. What we do is what we might call research, move that to operations, and then what we have are colleagues that say, you know what, that's really great, but we've just seen this thing. Or what we really need is to work out how to move our satellite safely from A to B. Well, what do we do if the comms are down? And they then pose us the challenges. And that's how we do operations to research. And then they can fund us. We can look at interesting other physics problems, but for a purpose. So it's research with an aim to deliver something that is useful to help mitigate this problem. So I guess what I'll finish by saying is that hopefully sometime soon you'll get to see the Northern Lights wherever you are. But the thing I'd like you to be sort of conscious of is whilst that's that really pretty thing that's really great and you should all try to see them, there are real things that are happening all the time. And whilst that May storm was going on and perhaps you were outside taking a photo, what I was doing on that evening was we were on almost 24/7 calls with people all over the world, operational centers, trying to make sure that the products, the services, the things that underpin modern society carried on working. And we're in a really good place doing that, but it is a core part of what we do. And Birmingham is one of the leading people that do that. And hopefully you find that interesting, and I'll be happy to answer some questions you may have. So thanks very much.
Sean, that was wonderful. Thank you. We've met a couple of times before, but I always enjoy hearing your presentations on this stuff. We've got questions coming through, which is we'll get those over to you now. But a couple of reflections from me. Nothing in physics is simple, I think you said. That was is interesting. The aurora, I went up to Lapland to go see those and missed. Could have gone to South Africa to see them. So that was note to self. Things are changing. GPS is slang. I had no idea. Yeah, this GPS is called something else, isn't it? So that was something else I learned. So thank you very much. First question from me, linked to the solar superstorms and the weather. The global pandemic had wide-reaching impacts in terms, and how likely is it that something really big and bad could happen, and what could be the impact of something significant?
Yeah, absolutely. So one of the motivations for this work done in the UK is that in 2011, 2012, space weather was added as a risk to our national risk register. So this is a collection of all the risks we think are facing the country, and what we want to do was work out how likely was this going to be. We need to prepare for it. And so a lot of studies have gone into that. And a really major significant thing, when we talk about power going out, I don't want people to ever worry. This is not a thing you should expect on a day-to-day basis, but this is a kind of 1 in 100-year event, which on the national risk register is exactly in the same line with a global pandemic. So when I used to talk about this pre-2020, that was somewhat more of an abstract concept to people. Now everyone's got a reference point. We know global pandemics don't crop up all the time, but when they do, they are major. And that same kind of probability, 1 in 100 years, is what we would expect for a major space weather event to occur.
So we need to be ready.
So it's about not panicking, but do prepare. I mean, that's the line we try and take with government. And that's hard, right? Because there's only so many times you can say prepare for something until you see it happen. So it's a constant communication battle to explain the risk, but also make sure that we are prepared as a nation and as a planet, because these things are global. They don't, they are not going to respect borders. They are global phenomena.
Right. Well, we're all very pleased that we have you that has a seat at the table to advise people on what we need to do. So we're going to switch things up a little bit and ask Rachel's question that Rachel very kindly shared in the chat. Are there any consequences for the companies who send these constellations into space when one of their satellites falls back to Earth and lands on someone's house, car, garden? So thank you, Rachel, for that question. Sean, what do you?
Yeah, I mean, that is an excellent question. Short answer is no. I'm sure there are absolutely no consequences, to be honest. Space is wildly unregulated. I mean, we have broad, peaceful use of outer space kind of treaties from the UN in the 60s, but essentially the landscape, the legal landscape that describes space and regulation is not, it's not out there. It hasn't been done yet. Space law and who is responsible for what still all needs to be defined. But it's a really good question because there are some really funny things about this in some ways. So to try and avoid, you don't want a satellite falling on the floor. Now, obviously, the vast majority of the Earth is not got anyone on it. It's mostly ocean, and when there's not ocean, it's mostly empty, actually. We take up, little small bits. But let's say it does, and we have examples of it falling in the garden. SpaceX were told that their satellites had to not land, re-enter the Earth, or hit anything with a probability of 1 in 17,000 of not happening. That was a threshold they were given, which sounds like, well, that's great. The likelihood is really low. And that's how they got regulation approval. Unfortunately, SpaceX also planned to launch 60,000 satellites, which means that if they only have 1 in 17,000 hit the floor, well, that means they're planning for 4 of them to hit the floor. So the number of 1 in 17,000 sounds like a small number, but if you do lots of a small number, it's still a significant number. So absolutely, regulation is still to be defined, and a lot of work needs to be done in that area.
Thank you, Sean. David, next question. David Wright asks, do we know why the May 2024 CME, the biggest for 25 years, didn't impact electricity supplies? Are we getting better at managing these, or was there another reason?
Yeah, I mean, really, very informed question. Very good. So it was the largest event we'd had in about 20 years. However, it wasn't particularly large. So we did some analysis that said it was about a once in a cycle event, about a 1 in 10-year event. So not insignificant, but certainly nowhere near the scale that we are actually planning for in terms of the real critical response. The problem is the terminology is really bad because on our scale, we call that an extreme storm. The one in May was the largest value you can get. It's called a G5. It's a 1 to 5 scale. The problem is, if that scale really existed, the things I'm interested in would be called G10s, but the scale doesn't go that far. And so we called it extreme, and that was a problem. The other thing is we are better at dealing with it. We have a 24/7 operations center in the UK that planned for this. We have additional resilience built into the national grid. We have monitoring of the grid. We have planning. So it was a mixture of not the biggest event that we're planning for, even if the communications, in the news around the time, you'd think that, the sky was falling down from the news media. And we are better at planning for it. So it was a combination of both.
Thank you, Sean. Right, the questions are firing in, Sean. We'll get through as many as we can. Ashok asks, how many projects do we have that's ready to go clean up all the junk? Do we have? Sorry, the question just moved. Do we have enough? Do we have any plans if no projects? I think you touched on this in the presentations. How's the cleanup? How's the cleanup going on?
Yeah, so the European Space Agency have a fairly broad program of clean space. It's called Clean Space. And I know the Japanese have also done a large part in this area. The UK itself, if I took a UK answer, we've experimented with a few different ideas. And whilst they sound wacky, they include harpoon gun firing of things to try and catch them. We've talked about nets and deployed those. But real aggressive targeting of those things, there's only a handful of those missions. And essentially what they are is, I talked about that giant big thing in space, this EnviSat. I'll pretend my phone is EnviSat. That sort of flying around is, and you send a satellite up, you grab it and you pull it down safely. But that's really targeted, right? You have to do a whole satellite launch to remove one piece. So we have a list. We have a list of the 50 worst things, and we want to slowly work through taking them down. So there is some effort, but it is not huge. What we are trying to do, going back to that first question, is a little bit about regulatory work. So people may know that there is a UN rule that says satellites have to re-enter within 25 years now. But recently, we did some work with colleagues across the UK and suggested, hey, that number's not right. We need to make it 5 years. So the new UN guidelines is a satellite should re-enter within 5 years of finishing to try and reduce the amount of stuff that's out there. So some satellite missions, but regulation, again, is the thing we probably need to improve fastest.
Great. Regulatory work is so important to try and keep up with the
It is. And
rapid
whilst
change in
obviously
technology.
I haven't had chance to talk about it, Birmingham also has people in the law department that worry about space. So, the great advantage of Birmingham is that we do bits of everything. So I've given you a very physics end stuff, but this kind of regulatory stuff is stuff we think about as well.
Great, nicely said, Sean. Right, another question. Is there a finite number of satellites at the various altitude levels can support?
Oh, I mean, that's an advanced question. The answer is yes. There is, at any given altitude, there is essentially an orbital capacity that is the most you can hold in that shell. And there's some debate about what that is. The only thing I would say is that you can pack those shells in very tight. The number of satellites I can have at 500 kilometers, and then what about the number of things at 500.2 kilometers? You can really pack them in if you need to. But yes, absolutely. In each orbital shell, there is a capacity, a max capacity. And that final thing I ended with the CO2 changes, that is changing the amount of orbital capacity in each shell. So whilst we plan for that, that is a thing that then changes over time. So yeah, there's some really interesting work about that, and I would suggest a Google of CO2 satellite orbital capacity should bring you to a paper that, if you're, to know that question, I'm sure you're interested in reading the journal papers. So you can type that in and you'll find some interesting stuff.
Thank you. Some great questions. I'm struggling to keep up. So here's a slightly different one for you, Sean. Can you provide a simple back of an envelope explanation of how the sun's corona gets so much hotter than its surface?
Well, now that is a hard question.
Sorry.
Yeah, no, it's fine. I mean, can I give a reasonable explanation for why that happens?
A large envelope.
Yeah, I mean, I think it is a reasonably large envelope. I mean, the reason it's a good question is because this is the kind of thing that we teach in about the fourth year master's course in space environment. I mean, but yes, I mean, the surface of the sun is relatively cool compared to the corona, but it's essentially to do when everything is quite sparse, temperature gets quite confusing as a concept, right? When we think about temperature, you think about touching a solid object, and that has temperature. But temperature is really a measure of energy. It's kinetic energy. It's how much stuff is vibrating and moving around. And the plasma, once it's, not so bound by gravity holding it together, is more dispersed. And so the temperature goes up because everything's moving faster. So it's on the edge. So sort of the rough answer to that is it's on the edge of what you really think day to day of temperature. But absolutely, the question is right. The corona is significantly warmer.
Have a moment, rest after that one, sure.
Yeah.
Does space weather affect Earth's climate, or are the two completely separate issues?
Yeah, okay. So there is what we believe is certainly true is I showed you the solar cycle moving up and down. What I didn't show you is that we've tried to extrapolate that to much longer timescales. Now that's really hard because I wasn't around that long ago. But what we can look at is radiocarbon dating of trees to try and extract background solar conditions. And what we can say is that absolutely the sun over its history is sometimes more active and less active than at other times. And we believe that does have an impact on the climate on Earth. What I would say, though, is also that is pretty small. So at the moment, the sun is actually quite active. And that has probably led to a fractional of a percentage impact on the change in our climate. The reason that's really hard is obviously right now we know that there are anthropogenic impacts on the climate, and the sun makes a very, very tiny part of that. But absolutely, there is definitely historical records that it works that way. And then, as I said, going the other way, then the anthropogenic impacts, the increase of CO2, in some ways changes space weather. By changing the CO2, it changes how the atmosphere evolves. So there is a bit of a two-way process that goes on with that.
Great. Thank you. So a question from Ian. What would the impact of an event similar to the Carrington effect of 1859 on power systems and GPS? So what would the impact of an event similar to Carrington effect?
Yes, so that could almost be a nicely planted question. So
Yes.
thank you. So what I haven't mentioned by name is our reference big event. I talked about severe space weather, and as Ian said there, the event we call the Carrington event in 1859 is the largest event we know, and our planning is based around one of those hitting today. And I think there was power and PN and GPS there. So GPS is sort of the easy one. We would expect loss of position, loss of being able to get a satellite position for up to 3 days. So not a small disruption, but a major outage for multiple days, which has a whole host of impacts. I mean, one of the reasons, as a small anecdote, I won't take too long on this, but the mobile phone grid in the US works by, your phone connects to a cell tower, a mobile phone mast, and there's some signal pass between them. The mobile phone mast has to keep accurate timing to deal with all the signals. And the way they do that is they have a GPS built into it because you get nanosecond precise timing out of it. If the GPS goes down, then what can happen is that over time, your cell tower clock stops working and that knocks out the mobile phone signal. In the UK, that doesn't happen because we've hardwired all of our mobile phone towers in. And so we're not reliant on GPS in that way. So loss of GPS, hugely impactful. In terms of power grid, that maybe is the key question. What would a Carrington-sized event do to the power grid? Now, Lloyd's of London, the insurers, did a study that came out earlier this year, which estimated reasonably significant impact to the grid globally, because it's a global problem, and the consequence of about $2.9 trillion of disruption and damage. In the UK is a more resilient power grid than almost anywhere in the world. We are a reasonably small country. We have a lot of central investment in the power grid. We have planning, we have mitigation. The national grid have a space weather person. We have a plan in place. We know which parts are more impacted than others. So we might see intermittent power outages, but even at a Carrington level event, the planning we believe in place means that we would hope to avoid any serious disruption, perhaps some local power outage, but not sort of nationwide. But other nations certainly probably worse or more impacted than the UK would be in that sort of reference Carrington event. And I should say, and I think this is, some way we can communicate this afterwards, if you are really interested in the impact on systems, there is a report that we wrote out of Birmingham, sponsored by the Royal Academy of Engineering, which essentially is called, severe space weather impacts on UK infrastructure. So if you want to learn about any of these things in more detail, there's quite a nice overview report. There's a full detailed one, and there's the one that we delivered to government, which is much shorter. So there is some interesting, accessible reading that can be done in this area.
Lovely. Thank you. We'll be sure to share links after the
Yeah,
call.
thank you.
Okay, so two more questions. I've got time for two more. So, great question from Mike. He asks, can individuals do anything to prepare for these occurrences? These.
Excellent. Yeah, I mean, okay, so this is a really interesting point because the National Risk Register covers a lot of risks, not just space weather, but a whole host of them. And actually, a little bit of home preparedness is never a bad thing to have. So I don't want to do any form of, doomsdaying, but general life advice is store some bottled water. That's always a good thing. And that's always useful because if you've got a long power outage for any reason, some water is good to have. And if it's really space weather related and normally power, the thing that we can do ourselves is that as people get things like solar panels, more solar panels on the roof than ever before, that is a great way to get power in your home. However, you normally, when you get them installed, have an option of whether you want to have a battery or not have a battery. You should always take the battery because it means the solar panel energy can be stored locally in your house. So those are little things, power, but some general preparedness around, water and supplies are always a good idea. And then I think the only other thing I would say is the great thing about having so many people on this call to talk about it with is just awareness, because ultimately, we get support and money from the government, and so having people aware, MPs aware, is really important way to generate it. So there's some really practical things you can do, and there's some more sort of abstract things, which is support things like coming to this event, which is really helpful.
Great, great advice. We'll all be actioning that. Store water and some
Water,
pound.
yeah.
Yeah, great. Thank you. So the final question. Sean, we spoke last week about a donation you received from an electrical engineering graduate at the University of Birmingham, a gentleman called Alan, and Alan is on the call this evening. So Alan, if you listen, I hope you're still here. Thank you for your donation. Alan's donation was used to support a PhD student, Josh, I believe his name was, to do some dedicated work on his PhD to follow a particularly interesting idea that you wanted to explore further in high frequency radar, I believe. Could you tell us a little bit more about that and the impact? Because it's worked out very, very well, hasn't it? So it'd be nice to hear about that project.
Yeah, absolutely. So, we've talked a lot about, I've talked a lot about mitigating the impacts of space weather this evening. But there is actually another thing you can do, which is if you can actually model the space environment really well, there might be new technology that you can get to do things. So, well, yeah, we want to mitigate things, we want to protect, but if there are also sometimes really cool ideas that we can try and exploit. The problem with an issue, let's not say problem too strong, an issue with some way of funding UK research in academia is that very often you have to have some track record. I apply for money in space weather, we do research, everything's great. If I put in a bid to, try and get some money to do some cancer research, I probably won't win that money because I don't have any history of delivering it. But that can actually get really close to home. So in this example, Josh was interested in how we could do a new kind of antenna design. And actually, if anyone caught it very quickly, there was a little picture of it in the bottom left on my last slide. But we wanted to work out, hey, could we do something a bit different, which we might be able to leverage into the future? And what we had is we had some money from Alan to support Josh, took a break from his PhD to do this bit of research where we really quickly both supported Josh's time and equipment, the resources to do it. We did a sort of rapid development prototype, went into the field, did some experiments, huge success. And then we were managed to propose it now into UK government and BAE systems as, hey, look, we've got this new idea. We've had some sort of pump prime funding essentially to show it's a goer. And now that has led to a really significant research program to the university and to sort of central government. I mean, it's become a government priority area of something that we could do. It appears in the defense spending review that was in the news a couple of weeks ago. I mean, these are the kind of things that actually some money to support these kind of sort of slightly wild ideas have led to, huge real benefits. And then also not just Josh, because then Josh is working on it in a postdoc. We work on it, and we can even, it's enough money now to bring in other people to work in this research area. So that's the kind of thing that we did with that money. And yeah, Josh has met Alan, and that was really great. And we're obviously incredibly grateful to him for his support.
Amazing. I love that story. Wild ideas, developing new technologies, and significant follow-in funding. It's a wonderful example of higher education philanthropy and exactly the type of work that the team love getting involved in with alumni. So call to action number two, everybody to think about their charitable giving, their philanthropy, and from a personal perspective, but also people on the call to think about charitable trusts and foundations that you're connected with or know, your employers, businesses that might want to invest in some really great ideas, research at Birmingham, because it can go on to achieve magnificent results that benefit us all. So right, the Q&A complete. Thank you everybody for the questions, and sorry we couldn't get to them all. They're still firing through. I can't get to them all, but we'll respond to them where we can, and maybe Sean, we can forward them on to you, and we can sort of collate responses and
I was just
share
going to say,
those.
if that is possible, because there's some which cross over with each other, we can make a sort of generic answer to some, which would help. Because there's some really great ones in here I've just been scrolling through seeing. So yeah, great. Thank you.
Brilliant, Gate. Thank you everyone for your questions. And thank you everyone for joining this evening. We welcome your feedback from the event. So a link will be sent through a short feedback survey. So we'll share that in the chat. We have lots more exciting events lined up later this year and into next year. Beautiful Brains, building the neurodiverse workforce. Look out for that one. How much is a year of life worth? Designing health systems for equity and impact. And Dinosaur Detectives, that one's got the best name, I think. Dinosaur Detectives, Birmingham's fossil finds and the story that they tell. Please do take the time to complete the survey, and thank you for attending, and hope you enjoyed tonight's event. And most importantly, thank you, Sean, for a wonderful, wonderful presentation, and thank you for doing so well with those excellent questions. And good evening, good night, everybody.
Good night.